Hello everybody, getting ready to lesson 4.6 part 2 of pre-calculus math today. Here's my email if you need to contact me. 4.6 part 2, graphs of other trigonometric functions. Your notebook has got 10 points today, and then your classwork has 50 points on your classwork sheet. Students, get your classwork sheets ready. And today's bell work, teachers. Here's today's bell work. Identify the domain, any intercepts, and any asymptotes of this function here. Same thing down here. Give your students 6 minutes for that. Okay, welcome back for the solutions of today's bell work. So domain here is negative infinity, positive infinity. X-intercepts here once we factor this down. X plus 4x minus 1 equals 0, so x equals negative 4 would be an intercept, and then x equals 1 would be an intercept. Here's your intercepts for this function here. The y-intercept would be 0, negative 4. There are no asymptotes for this function here. And then for 88, domain all reals, x cannot equal 0 in a log function. X-intercept would be x equals 1. And x equals plus or minus 1 would be a x-intercept for that. And then here it is in coordinate ordered pair form. Y-intercept is none. Vertical asymptote will be 0. So into your notebook, students, have your notebooks out, have your notebook guides out. Graphs of the reciprocal functions. The graphs of the two remaining trigonometric functions can be obtained from the graphs of the sine and cosine functions using the reciprocal identities. Cosecant x equals 1 over sine x and secant x equals 1 over cosine x. For instance, at a given value of x, the y-coordinate for secant x is a reciprocal of the y-coordinate for cosine x. Of course, when cosine x equals 0, the reciprocal does not exist. Near such values of x, the behavior of the secant function is similar to that of the tangent function. The graphs of tan x equals sine x over cosine x and secant x equals 1 over cosine x have vertical asymptotes at x equals pi over 2 plus n pi. So there's a similarity here between tan x and secant x, where n is an integer, that is, the values of which the cosine is 0. So when your cosine is 0, you have a vertical asymptote. Similarly, cotan x equals cosine x over sine x and cosecant x equals 1 over sine x have vertical asymptotes when sine x equals 0, that is, at x equals n pi. To sketch the graph of a secant or cosecant function, first make a sketch of its reciprocal function. For example, to sketch the graph of y equals cosecant x, first sketch the graph of y equals sine x, then take the reciprocals of the y-coordinates to obtain the points on the graph of y equals cosecant x. You can use this procedure to obtain these graphs here. So down here you have sine x, y equals sine x here, f of x equals sine x, and then f of x equals cosine x. So when you do this, where they top out here, you put on your secant curve here on these, inside these two vertical asymptotes, and then over here for your cosecant graph, you graph your y equals sine x, and then where it tops out here and bottoms out here, your max and your min, this is where your cosecant curve will come in and hit it, and then go back the other way. And so that's a great way to do it by hand. And so here we are again with our cosecant graph here. And then domain, all reals, range, negative infinity and negative 1, with the union here of 1 and infinity for our range. So we have a range that's limited between here and here. You have no range here between negative 1 and 1. And then the period here is 2 pi. There's no intercepts. Vertical asymptotes are x equals n pi. It's an odd function with the symmetric to the origin. And then we have here your secant is the stipulations for that. Domain is all real numbers. X cannot equal pi over 2 plus n pi because that is your vertical asymptotes here. Range is negative infinity and negative 1. So it comes up to here and it goes back down to negative infinity. And then up here you have infinity comes down to 1 and goes back to infinity that way. We got the vertical asymptote. It's an even function. It's symmetric to the y-axis. It has symmetry here because it does have a y-intercept here, is why. It uses the y-axis as symmetry. Okay, our next classwork slide here, page 5, and comparing the graphs of the cosecant and secant functions with those of the sine and cosine functions. Note that the hills and valleys are interchanged, so you have your sine function here, and then here's your cosecant here, which tops out contacting your sine function here. Are interchanged, a hill or a maximum, so this would be a hill here on the sine curve. So this would be a hill here on a sine curve. Corresponds to a valley of the cosecant curve, and a valley or minimum on the sine curve corresponds to a hill or local max on the cosecant. So that's why they have something going on here. Additionally, x-intercepts of the sine and cosine functions become vertical asymptotes. So the x-intercepts here of the sine function, these are your vertical asymptotes here of the cosecant and secant. So they do definitely have an interrelation there. Sketch the graph of y equals 2 cosecant quantity x plus x over 4 by hand. So by sketching a graph of y equals 2 sine x plus x over 4 for this function, the amplitude is 2 and the period is 2 pi. By solving the equations, x plus x over 4 equals 0 and x plus x over 4 equals 2 pi. You can see that one cycle of the sine function corresponds to the interval from the graph of the sine function. So is represented by the gray curve. So here we have this situation here, y equals 2 sine of this here. This is your sine function here. Then your cosecant, again, it contacts the max and the mins of your sine function is where your cosecant comes down and contacts it like that. So that's what really makes it cool, where these two functions are interrelated in that manner. Because the sine function is 0 at the endpoints of this interval, the corresponding cosecant function, y equals 2 cosecant x plus x over 4 equals 2 over 2 times 1 over sine x plus quantity x over 4. So they definitely have a relation here like that. Okay, so it has vertical asymptotes at negative x over 4, which would be here, and then x equals 3 pi over 4 would be another vertical asymptote, which would be here, and then x equals 7 pi over 4, which would be here. So you have vertical asymptotes at each one of these points here, which is where your sine function intercepts the x-axis here. The graph of the cosecant function is represented by the black curve. So this is your cosecant function here, down here, and up here. Let's try one of these. We have y equals 3 cosecant x over 2. So the graph in our period here would be 2 pi over 1 over 2. So it'll be 2 pi over 1 over 2, which will be 4 pi. We have two consecutive asymptotes. X over 2 equals 0, so x would equal 0. So we have a vertical asymptote on the y-axis, and then x over 2 equals pi. So x would equal 2 pi. That would be our second asymptote there. Here's your table for this function here. And then once we plot that in, we get something that looks like that here. This is without graphing the sine function to do this. We're just doing it right from our table as well as your graphing calculator to come up with your vertical asymptotes as well as the actual curves themselves. And then down here for negative cosecant x over 3, we have 2 pi over 1 over 3, which gives us 6 pi as our period. So we have two consecutive asymptotes here at 0 and 3 pi would be our vertical asymptotes. Here's your table for this function here. So these are pretty fine numbers, and then this is what it should look like here. We have a asymptote here at the y-axis, and then over here at 3 pi would be our next vertical asymptote there, and then etc. to the left and to the right. Then this would be 7 pi over here like that. So that would be how you would have an idea of what this graph looks like here. Negative 3 cosecant x over 3. Okay, let's go into another example here. F of x equals secant x. So sketch the graph of y equals secant 2x by hand. So begin by sketching the graph of y equals cosine 2x. So this will be your approximation here of the y equals cosine 2x as indicated by this gray curve. What they call a gray curve here is this curve here. So start by graphing your cosine 2x so we can graph the secant 2x by hand. That'd be the way to do it by hand. Now for your y equals secant 2x, you just go ahead and latch on to your mins here, and then your max is up here. We have a half of a curve there, and then we know our vertical asymptotes are there. So by graphing again our sine x, which is a little bit more knowable and friendly, we can just latch on to that. And then we have symmetry here to the y-axis. Note that the x-intercepts of y equals cosine 2x is negative x over 4, which would be here, then x over 4 would be here, and then 3 pi over 4, which would be here. Those would be your x-intercepts. Again, this is where the sine curve intersects with the x-axis as well. Again, there's our graph of our function. So they correspond to vertical asymptotes, negative x over 4, then 3 pi over 4. We got that. So corresponding vertical asymptotes is the graph of y equals secant 2x. Moreover, notice that the period of y equals cosine 2x and y equals secant 2x is pi. So the periods are similar too between these two functions. So they definitely have interrelation there. Sketch a graph. So we have secant pi x minus 3. Down here we have negative 2 secant 4x plus 2. So shift the graph of secant pi x down 3 units. This is going to shift it down 3 units for a secant pi x. And then we have we need to find our two consecutive asymptotes. So for that, our period here is 2. We have a period here of 2 because of our number here. So it gets shifted down 3 units. So here are our vertical asymptotes. will be negative 1/2, and then x equals 1/2. So negative 1/2, and then positive 1/2. So this would be our consecutive vertical asymptotes here. Negative 1/2 and 1/2, and then again would be 1, and then negative 1. Those would be our vertical asymptotes. This would be our first part of our secant curve here, would be this piece here. And our second one will be down here. We have a shift here down -3. So we're down here at -4. So we're going from, usually our sine curve goes something like this. That would be our sine curve in there. So it would help you if you graphed your sine curve. That would help you plot these things by hand here. And then our half is over here. Then we have a half over here as well. That would be this function here, because we have a drop here of -3. Okay, on to our notebook. Damped trigonometric graphs. Product of two functions can be graphed using properties of individual functions. So a product here of two functions. For instance, consider the function f of x equals x sine x as a product of the functions y equals x and y equals sine x, using properties of absolute value and the fact that the absolute value sine x is less than or equal to 1. You have 0 is less than or equal to the absolute value of x multiplied by the absolute value of sine x is less than or equal to the absolute value of x. Consequently, the negative of the absolute value of x is less than or equal to x sine x is less than or equal to the absolute value of x, which means that the graph of f of x equals x sine x lies between the lines of y equals negative x and y equals x. Okay, so furthermore, because f of x equals x sine x, which equals plus or minus x, at x equals pi over 2 plus n pi, and f of x equals x sine x equals 0 at x equals n pi, you can see you're going to come up with something like this. When y equals negative x, this is an identity function line here for negative y equals negative x, and then here is an identity function for y equals x. We're using this as a container for this curve here to keep it inside this curve. It's very much like an integration of calculus. The graph of f touches the line y equals negative x or the line y equals x at x equals pi over 2, which, where would it be? If x equals pi over 2 would be here, so it touches this line at pi over 2. See, y equals x at pi over 2, that would be this line here, so it touches it here, and has x-intercepts at x equals n pi. So here we have n pi, intercept here, and intercept there. A sketch of f is shown. So we're showing f of x equals x sine x, which is this thing here, which is contained within these identity functions here. F of x equals x sine x, the factor x is called the damping factor. So the damping factor here is the factor x is called the damping factor. So we're damping it by x here. So what are we going to do with that? Well, what's the whole point of that? Analyzing a damped sine curve. Analyze the graph of f of x equals e to the negative x sine 3x. So consider f of x as a product of two functions, y equals e to the negative x and y equals sine 3x, each of which has a set of real numbers as its domain. So each one of these has real numbers as its domain here for this function and that function. For any real number x, you know that e to the negative x is greater than or equal to 0, and the absolute value sine 3x is less than 1, so e to the absolute value e to the negative x, and then the absolute value sine 3x is less than or equal to e to the negative x, which means that here we have our statement here with all these preconditions here. You end up with this here. What does that look like in a graph? Furthermore, because f of x equals e to the negative 3x sine 3x equals plus or minus e to the negative x at x equals pi over 6 plus n pi over 3, and f of x equals e to the negative x sine 3x equals 0 at x equals n pi over 3. The graph of f touches the curves y equals negative e to the negative x and y equals e to the negative x at x equals pi over 6 plus n pi over 3 has intercepts at x equals n pi over 3. So this would be your damped function here. Thanks to our e function here, it contains this sine curve here by these two e functions. Y equals e to the negative x, which is this function here, and then the negative e to the negative x is down here, which damps this sine curve here. So let's try one. Using a graphing utility to graph the function and the damping factor of the function in the same viewing window, then analyze the graph of the function using the method in example 6. So we have e to the negative x cosine x. So for this one here, the damping factor is e to the negative x. We're going to use this as our damping factor. And then we're going to take the negative of that, e to the negative x is less than or equal to e to the negative 1. Cosine x is less than or equal to e to the negative 1. So y will equal plus or minus e to the negative 1 touches y equals e to the negative 1 cosine x at x equals n pi. Then y to the e to the negative x cosine x says x-intercepts at cosine x equals 0, or x equals pi over 2 plus n over pi. So this would be what this would look like, cosine x with a damping factor of e to the negative x. This is what that would look like here. So trigonometric functions, this is our sine curve there, this is our cosine curve there, and then this is our tan function, this is our cotan function. This goes in your notebook, students. Make sure you get this down. If not, go to YouTube or PowerShow to get these down. Teachers, make sure they get that down. Then continue on here, cosecant x. This is our cosecant function. And then this is our secant function here. And that is your 4.6 part 2. Email me here for questions or materials for pre-calculus math. Thank you very much.